This is the mock exam for applications of calculus, including kinematics. First problem is a applications of differentiation problem and optimization problem. Very typical for optimization problems. It's about area. A farmer wishes to create a rectangular enclosure ABCD of area 135 as shown below. The fencing used for side AB costs $7 a meter. The fencing for the other three sides costs $3 a meter. The farmer creates an enclosure so that the cost is a minimum. Find this minimum cost. Okay, so first of all, I'm going to write the price per meter on each side. So it's 7 if it's AB, and the other ones are all 3 each. Okay, so this is the cost, so I'm going to put dollars next to it. And then we are going to figure out the length of each side to make the cost a minimum. And so let's call the widths X, and we'll call the lengths 7, or I don't know if you'd call that the which would be the length and which would be the width, but whatever. Okay, doesn't matter. All right, so we're going to first write a cost function. The cost is equal to each one of the sides times its per meter fence cost. So it would be 7x, which is the bottom one, plus 3x, which is the top one, plus 3y, which is the left side, and 3y, which is the right side. That's the cost function. Then we also have an area equation. Usually you have like a perimeter related equation and you have an area related equation. So here are the two equations. Area is always equal to x times y. In this particular case, we also know that the area is 135, and it's always 135, so we'll go ahead and write that down. Now we need to figure out which one of our equations is the cost, which is the optimization equation, and which one is the constraint equation. What's the difference between the two? Well, the optimization equation is the one that you are trying to minimize or maximize, so we already know that the cost equation is the optimization equation. So the other one is the constraint equation. Usually the constraint equation only has 2 variables in it, and it looks like we have 3, but we've eliminated the a variable because we know that xy is always equal to 135, so it doesn't matter that it's also equal to a. We can eliminate a. So now we have xy equals 135, the constraint equation, and we have this other long equation for c. We could simplify c first of all. We could say c equals 10x plus 6y. That makes it a little easier. What we need to do now is we need to get rid of either x or y so that we have a 2-variable optimization equation, and that's how we can figure out either x or y so that c is maximum or minimum. In this case, we want minimum. How do we do that? We eliminate it with a variable from the constraint equation. So what we're going to do is we're going to solve for one of the 2 variables. It doesn't matter which. So I'll solve for y. And we get an expression which we use to eliminate. Is this a highlighter? Yes. We're going to eliminate the y's by substituting this in to every occurrence of y when there's only one. So now what I'm going to do is I'm going to rewrite c, and I'm going to eliminate y by writing 135 divided by x next to it. Okay, now I have c equals 10x plus 6 times 135 divided by x. 6 times 135, this is a non-calculator problem. Oh my gosh, so it's going to be 600 plus 180 plus 30, so that is equal to 810 divided by x. Okay? All right. Now what am I going to do? Okay, since the optimization equation has been reduced to 2 variables, c and x, I can take the derivative of c with respect to x, which gives me c dash equals 10 plus, and remember, 810 divided by x is the same thing as 810 to the x times x to the negative 1. Taking the derivative of this, we'll get 810 times negative 1 times x, and then we'll reduce the negative 1 to a negative 2. Now we can rewrite c dash, so it's 10 minus 810 x to the negative 2. it's 810, not 816. Okay. Ugh, that's terrible. Okay, now what I'm going to do is I'm going to rewrite it again with x squared in the denominator, because now it's easier to solve in this format. I'm going to set the derivative equal to 0 because the maximum and minimums always occur when c dash equals 0. Now I'm going to add 810 over x squared to both sides to move it to the right. Now I'm going to cross multiply to get x squared in the numerator. Okay, and then I divide both sides by 10. That gives me x squared equals 81. Whoa, x squared equals 81. That's a perfect square. X equals 9. Okay, if we know that x equals 9, then we know that y equals 135 divided by 9. And we don't have a calculator, but if we did long division, we would find out that that's equal to 15. Okay? Yeah, 15. All right, now we have x and we have y. What did we actually want? We want the minimum cost. So the minimum cost we can find by taking x or y, or both, and putting them into c. So c is equal to 10x plus 6y. Since we already have our y and we have our x, we can just put them directly into the original equation. So it would be 10 times 9 plus 6 times 15. 90 plus 90 equals 180. So our cost, minimum cost, is $180. We're done. Okay. Let's go to the next problem. This problem is, and again, calculator not allowed. Forgot to mention in this first problem, calculator not allowed. Okay, the following diagram shows part of a graph of a function, f of x equals 2x squared. Of course, they're talking about this curved part, not about this straight part. Okay? The line t is the tangent to the graph of f at x equals 1. Okay, so this line here is a tangent line, only touches the parabola at one point. Okay. Now, this is optional because this is really from last unit, and I don't want to waste time on the mock exam with stuff from the last unit. Unless you wanted to do it for practice, that would be fine. So it says, I'm going to show you how to do it here anyway. Show that the equation of t is this. Okay, remember t is the tangent line. How do we find a tangent line again? Well, first of all, we start with the formula from the formula sheet, which is point slope form, y minus y1 equals m times x minus x1. First of all, what goes into x1 and y1, the point at which we're going to find the tangent line to, we know that we want to find it at x equals 1, so we're going to put 1 in there. What would be the y value that goes with x equals 1? We just put it in here. It would be 2. So this point here happens to be 1, 2. So we'll put 2 there. The only thing we need now is the slope. The slope of a tangent line is equal to the derivative at the point x equals 1. So all we need to do is find the derivative of f of x equals 2x squared. That would be 4x, wouldn't it? So f dash equals 4x because we just took the power rule of 2x squared. Now we are going to substitute in x equals 1 so that we can get the slope at the point x equals 1, and we get 4. So we can put 4 here. Now we have everything. Y minus 2 equals 4 times x minus 1. It wants us to show that it's y equals 4x minus 2, so we just need to do a little bit of algebra and rearrange it. So we get 4x minus 4 and plus 2 because we add 2 to both sides. Y equals 4x minus 2, so we have demonstrated that it is indeed 4x minus 2. Find the x-intercept of t. So where is this point here? Okay, the way we can find that is we know that the x-intercept has a y coordinate of 0. So we could put 0 in for y, so we'll do that. 0 equals 4x minus 2. Well, let's rearrange it. 4x equals 2. X equals 2 over 4. which is equal to 1/2. So that means that this point is 0.5, 0. That is the x-intercept of t. We're going to find out why they asked us for that. The shaded region R is enclosed by the graph of f, the line t, and the x-axis. Okay, let's figure this out. They said the shaded region is enclosed by f, line t, and the x-axis. Yeah, that's true. It is bordered by those three curves / lines. Write down an expression for the area of R. What they want here is an integral expression, because integrals are used to calculate area, if you remember. Okay, so there's two approaches we can use. Maybe the easier approach, which is maybe harder to see, is you take this shape here and you subtract out this blue triangle. So let's do that. What is the integral expression to find that red shape? So what we're going to do is we're going to take the integral from 0 to 1 of the function f. Let's write that down. 0 to 1 of the function f. And then we're going to subtract the triangle. And the triangle, if we want to use an integral, would be the integral from 0.5 to 1 of 4x minus 2. Let's do that. 0.5 to 1 of 4x minus 2. Okay? Now all I need to do is write in what is the expression for f again. It is 2x squared. So I'm going to rewrite this. I'm going to say 0 to 1, 2x squared minus, and then I'm going to put the blue expression, which is the integral. Oops, I was going to do blue, but whatever. 4x minus 2. Oops, I forgot to write dx here. Be sure to write dx, okay? All right. Now I have an expression which would give me the shaded region if I integrate it. Now I'm going to write the alternative. The alternative is maybe the one that we see after doing a whole bunch of integral problems. It's dividing this into two sections, okay? We need to divide it into a section which is basically just the derivative or the integral of the function f. Then the second part is a little bit more difficult because we're going to take the function f and we're going to subtract out the white triangle, which is 4x minus 2. It's the other function. Okay? So if you think about it, this part here is just the integral of f. This part here is the integral of f minus t. Okay? So let's write that out. Oh, and by the way, the limits in each case, this would be the limit from 0 to 0.5, and this would be 0.5 to 1, because we know the intersection point. Ah, that's why they wanted us to figure out the intersection point. Okay. So the alternative is 0 to 1/2 of f. And then the other part is we're going to add it to 1/2 to 1 of f minus t. Now we're just going to fill in some stuff, okay? So 0 to 1/2, and we're going to fill in f, which is 2x squared dx. And then we're going to add it to 1/2 to the integral of 1/2 to 1 of 2x squared minus the t expression is 4x minus 2 dx. Okay, so that is the two possibilities. Okay, all right. Now find the area of R. Okay, so this is not a really difficult integral to do. Either one is going to be give you the right answer. So let's just do this first one. So first of all, the integral of the left side would be x cubed divided by 3. The integral of x squared is x cubed divided by 3, and we're going to multiply that times 2. So it would be 2x cubed divided by 3, and we're going to evaluate it from 0 to 1. The other part is going to be, let's see, the integral of 4x is going to be 4x squared over 2. The integral of -2 is -2x. We're going to put it in parentheses. Actually, it's kind of handy to use the brackets that are from the book notation for taking the definite integral. And then we'll put 0.51 here. Oh, by the way, yeah, that's right. Okay. We can cancel that out. It's 2, right? So let's do the left expression first. So we're going to substitute 1 in for x, and we get 2/3. If we put 0 in there, we get 0. So there is our simplified version of the left expression. Now let's do the right expression. 2x squared minus 2x. And we're going to first substitute in 1. So we put in 1 for x squared. We put 1 in for x. So we get 2 minus 2. Okay. Then we put 0.5 in there. And then we'll get 0.5 squared is 0.25. 1/2 squared is 1/4. So we get 2 times 1/4 minus 2 times 1/2, which is 1. Okay, so now we have 2/3 minus, and this is a 0, and then 1/2 minus 1 is -1/2, but we take the negative of that, so it would be positive 1/2, and then we take the negative of that, and it'll be -1/2 again. And then we have 2/3 minus 1/2. Everybody knows that's 1/6, right? Not true. Okay, so let's convert these to a denominator of 6 in both cases. 2/3 is equal to 4/6. 1/2 is equal to 3/6. 4 minus 3 is 1, so that's equal to 1/6. Okay? All right. Let's move on. Number 3. Thank God. We're back to the calculator. Let me rearrange the screen and put the calculator on here. Okay, here we are on number 3 where the calculator is allowed, and this problem is quite similar to the previous problem except for we can use a calculator to do it. Okay, that's why I included it. I wanted you to see a paper 2 problem versus a paper 1 problem. Don't waste your time doing any of a paper 2 problem without the calculator. They don't want you to do that. Okay, so let's take a look at this one. The following diagram shows the graphs of function f and function g for the domain x is between 1 and 10. Let A be the area of the region enclosed by the curves of f and g. Okay, what do they mean by enclosed? Well, the area that's enclosed by f and g is only this part here. What about this part here? It's not enclosed because you notice that they cut it off right there, and when they cut it off, no longer closed, so it's not enclosed, is it? Not this part either, so we're just talking about that middle part, okay? What do we need to do to find this area? Well, first of all, we're going to do an integral, right? But when you do an integral, besides knowing the functions which are involved, which we do, g and f, you need to know where the integral starts and where it ends, which is the x value of the left intersect and the x value of the right intersect. Well, don't waste time trying to find these intersections without the calculator because that is one of the best things that the calculator does. So first what we're going to do is we're going to program the calculator so that it's got function f and it's got function g in it so that we can find the intersection points. So we're going to type in natural log parentheses x 3x minus 2 plus 1, and that's our y1, and our y2 is going to be -4, not minus 4, -4 cosine and 0.5x. Oh, and speaking of cosine, we do need to change our calculator mode to radians, because whenever you have a problem like this, the domain or the mode should be in radians. Okay, so let's do that. We're going to go to mode. And we're going to go down to this 4th row here. And oh, it's already in radians. That's good. The default mode for the calculator is radians, and that's kind of handy when you want radians. All right, there is y1 and y2. We're going to go back there, and then we're going to graph it. And I think probably, yeah, see, the nice thing about the scale that they use, x equals 0 to 10, y equals 0 to 7, is it appears when you first run when you do zoom standard, right? And this does not look good. I think that I typed in something wrong. Let's check. Yes, the cosine. Oh, I forgot the x value. You guys probably saw me do that, and you're like, oh my gosh, headed for disaster. Don't worry. I'll figure it out. All right. It's nice that they provided the graph, and then you can compare your graph on the calculator with their graph, and you can easily see that you did something wrong when you do. Perfect. Now we're trying to find this little space here between the blue and the red. To do that, we need to find the intersection point, so let's do second calc intersect. Remember good old second calc intersect? When you do second calc intersect, it asks you to say the first curve, second curve, and guess. Since I only programmed y1 and y2 in there, there's only those two curves, so I just hit enter twice. First curve, yes. Oh, you know, this is a kind of a pegadinha. So, did you notice that the cursor is in the middle whenever you start a second calc intersect? And look, the first curve doesn't exist at x equals 0. So, this is the pegadinha. So, when you hit enter to choose the first curve, it does nothing. So, what do? You use the cursor moving thing, arrow, and then you move it so that it finally appears on the blue curve, and then you hit enter. And then you hit when it's second curve, then it's fine because the second curve exists everywhere. So that's kind of a pegadinha. So if the cursor is in no man's land, it's not on top of the function, it won't allow you to actually choose the function. So then it says guess. And remember how I always said guess didn't matter? Well, guess doesn't matter if you only have one intersection. If you have two intersections, you need to put the cursor closer to the intersection that you want. Well, it's already closer to the left intersection, so I'm just going to hit enter there. And it says the intersection is 0.688, I rounded. .688. Oh, it found a weird intersection. I want that intersection. 0.688, it doesn't intersect there. Okay. Second calc, maybe it's imagining like, okay, yeah, I get it. So it didn't show you, but like, do you see how the log curve actually goes down here? Okay. It actually has like an asymptote. It's just not showing up there because I think it's incapable of graphing such a vertical line. Okay, so we're going to do second calc intersect again. 5. And then first curve, yes. Second curve, yes. And then we're going to put the cursor closer to... Actually, we could just type in 3, right? 3. Okay, now it gives us the right guess, which is, or it gives the rest the right number, which is x equals 3.77. What about this one? And we're going to repeat again. Second calc, intersect, number 5. And then we're going to do first curve, second curve again. Okay, second curve. And then we move the cursor this time closer to the other point. Okay, it's really slow. So what I'm going to do is I'm just going to type in the number 8. And there it is, 8.30. 8.30. Those are the two x values which are going to be the limits of my integral. And then inside the integral, I'm just going to do g minus f or f minus g. Which is it? G minus f or f minus g? Well, do you see how f is on the bottom and g is on top? So we want the area to be positive, so we do g minus f in between these 2 points. So we're going to have the integral from 3.77 to 8.30 of g minus f. And g is -4 cosine 0.5x plus 2 minus, and then we're going to put the log function in parentheses because we have to distribute the negative sign later. Okay, dx. Okay, and now we are not going to take the integral of this, okay? Maybe you might not realize this. We don't know how to take the integral of log anyway. Okay, so now what we're going to do is maybe simplify a little bit so that we can put it in the calculator easier. We can combine these two. This is plus 2, and this is actually minus 1, because see, there's a negative here. So plus 2 minus 1 gives us plus 1. Minus times natural log of 3x minus 2 is negative natural log 3x minus 2. And then negative 4 cosine of 0.5x is just that. Okay, and that's the integral with those limits. Let's plug it into the calculator. How do we do that? We're going to put this into y equals, and then we're going to do second calc integrate on it. So let's do that. So we're going to put negative 4 cosine 0.5x close parentheses plus 1 minus natural log. Oop, they already have parentheses. 3x minus 2. And that's it. Now we're going to do second calc intersect, which is number 7. And it's kind of weird. This yellow area here is going to get smashed onto the x-axis. So it looks kind of similar, but instead of being floating like that, it's going to get smashed. And that's what's there. That's why it doesn't look like that anymore, because we did actually the cosine function minus the log function, which makes it smashed against the x-axis. So now when we do the integral, when we do the lower limit, upper limit, we type in our lower limit, 3.77. We hit enter. And then we do our upper limit, which is 8.30. Hit enter. And then it'll color in exactly the part that's smashed against the x-axis. And it says our answer is 6.46. So the answer is 6.46. All right? That wasn't too bad, was it? Let me show you one other way to do it on the calculator. This one I don't like quite as much because you can't check to see your area is as you expected it to be. So you do math. And we look for number 9, which is function integrate. Function integrate. And basically you just fill this in. It makes it look exactly like the integral. That you just did here. So it would be negative 4 cosine 0.5x plus 1. Oops. Plus 1 minus natural log 3x minus 2. Oops, 3x minus 2. And then dx. And do I have an extra? No, that's fine. And then I hit enter, and it gives me 6.46 also. Okay, so that's another way to do it. Doesn't have the nice graph. All right, that's it.